My project is about comparing these 5 sorting algorithms, but why is sorting important?
Hi, my name is Aditya, and I'm a student at the North Attleboro Middle School, and I'm doing a programming project on the efficiency of sorting algorithms, and that's why I'm here at the Richards Memorial Library that houses more than 45,000 books.
So, say you were trying to find a book in the library called iFunny by James Patterson. Well, libraries are usually organized in 3 categories: children's, young adults, and adults. And then inside of those, they're organized into fiction and nonfiction, and then they're organized by the author's last name. So, if we're trying to find this book, first we'd find the children's section, which is where I am. Then you'd find the P for Patterson, and then you would search through that until you find the book. So, imagine if you had to find this book in a library that was not sorted. It would take forever. And we might be onto something here. Really fast search engines like Google employ the same technique. They sort their data before they search. This is why they can find millions of results for any search in under a second.
So, how do sorting algorithms actually work? Well, bubble sort, one of the simplest sorting algorithms, works like this. So, you compare adjacent numbers. 3 is not bigger than 9, 9 is not bigger than 10, 10 is bigger than 7, and 10 is bigger than 6. This first pass means that the largest number has bubbled up to the right. 3 is not bigger than 9, 9 is bigger than 7, and it is bigger than 6. Now, in the second pass, the top 2 largest numbers have bubbled up. And you keep repeating this until you have a completely sorted list.
Another sorting method is called selection sort, and it works by dividing the list into 2 subsections of unsorted and sorted. It then tries to find the smallest value in the unsorted list. 3 is smaller than 7, 12 is not smaller than 3, and 9 is not smaller than 3. And so 3 is moved over as the first value in the sorted list. It then continues with this and keeps going on with the second, third, and fourth passes. Once all the numbers have been moved over to the sorted side in order, that is the final output of the list. In terms of efficiency and how good of an algorithm it is, it's about equal to bubble sort, but it is less efficient and slower than insertion sort, comb sort, or quick sort.
This is quick sort, and it's the fastest of all sorting algorithms. I wrote this flowchart to explain my code. At first, it finds if the list size is greater than 1. If it is, it makes the middle number the pivot. Then, for each of the numbers in the list, it compares it to the pivot. If they're smaller, then it moves it to the left list, and if they're bigger, it moves it to the right list. Once each of the numbers have been either moved to the left list or the right list, it sorts either of these lists recursively using the same code. At the end, you have a bunch of lists with only one number in it, all sorted in order, and you combine them to make the final sorted list.
This is my code. I wrote it in a language called Python, and I wrote it in an editor called PyCharm. As you can see, all of my programs are on the left-hand side: bubble sort, comb sort, insertion sort, quick sort, and selection sort. I wrote all of this code myself, and I did not copy it nor download it. But I did learn the algorithm theory from other sources. So this is bubble sort in a little more depth. If a list consists of 5 numbers, for the first pass you have to do 4 comparisons, for the second pass 3 comparisons, and so on, and you have to do 4 passes. So, generalizing, for an array of size n, there will be n-1 comparisons and n-1 passes, which is about n squared operations. Comparing this to other sorting algorithms, selection sort and insertion sort also have n squared operations, and because all of them are in-place sorting algorithms, they require low memory usage. Comb sort, despite having n log n operations, also is in place and requires low memory usage. Quicksort, in worst case, has n log n operations, but in best case has just log n operations, but it uses many lists, which means it has high memory requirements. I compared all of these different sorting algorithms with n squared divided by 2 by how many comparisons of numbers was required. Bubble sort, selection sort, and n squared divided by 2 required a large amount of comparisons. Insertion sort was akin to about half, and comb sort and quicksort was very low. And if you put this on a line graph, bubble sort and selection sort were similar. Insertion sort was low, but not quite low enough. And comb sort and quicksort were at the bottom of the chart. If you compare this in the list sizes like before, by time this time, you find that bubble sort took about 2 hours, selection sort a little over an hour and a half, insertion sort took about an hour, and comb sort and quicksort took under a minute. This shows that quicksort was the fastest, comb sort was the second fastest, and insertion sort was the third fastest. This is applied and used in search engines like Google, Bing, in database indexing, and search indexing. I contacted experts in the field of computer science. Dr. David Koken told me to comment my code better and to plot the time in minutes so it's easier to understand. Dr. Yuping Wang told me to look into memory usage and to learn about indexing. These are my citations and the sources I used.
When I started this project, I didn't realize just how hard sorting algorithms were. Well, it turns out really hard. I have renewed respect for sorting algorithms and how vital they are in this world, where mind-bogglingly large amounts of numbers need to be sorted instantaneously. An interesting fact is that Sir Tony Hoare's quicksort that was invented years ago is still being used today and is one of the top choices for things such as search engines. On a bit of a personal note, through this project, my array operations in Python have gotten a lot better. Thank you for listening.